When the 777X rolled out, its wings were too good. So long, so efficient, so optimized that they simply didn't fit at most of the world's airports. So Boeing did something no modern airliner had ever attempted. They designed wings that fold. Today we're breaking down the engineering story behind the Boeing's 777X's folding wingtips, why Boeing needed them, how the system works, and what makes this aircraft fundamentally different from anything flying today. This is the innovation that allowed Boeing to chase extreme efficiency without redesigning the entire world's airports. Before we dive into the 777X folding wings, hit like and subscribe to JetLogic. You won't want to miss the engineering behind the world's most advanced jets. Wings are the heart of any long-haul airplane. Bigger wings mean higher aspect ratio. That's just wingspan squared divided by wing area. And higher aspect ratio is the aerodynamic secret sauce that slashes induced drag at cruise. Less induced drag equals less thrust needed equals lower fuel burn over long flights. In plain terms, longer, skinnier wings make the airplane sip, not gulp, fuel. But wings don't live only in the sky. They also have to fit on the ground. Airports, gates, and taxiways were built to decades-old ICAO FAA design codes. Those codes divide aircraft into groups, Code E, Code F, etc., and tell airports how much real estate a jet needs at the gate. A super efficient wing can be useless if it turns a plane into a tarmac monster that won't fit the gate. Enter the 777 family. The 777-300ER set the baseline for big twin-engine long-haul. With the 777X, Boeing wanted a leap, a new composite wing plus the GE9X to cut fuel burn. The catch? The wing they needed was longer than many airport gates could handle. Shrink the wing and you lose the efficiency, force airports to rebuild, and you bankrupt route flexibility. So Boeing picked a third path. Keep the long, efficient wing in flight, but fold the wingtips on the ground so the plane behaves like a Code E airplane. That's the practical move that makes the whole airplane work. But that practical solution came with a price. Because the moment you add a moving part to a commercial jet's wing, you invite failure, complexity, and scrutiny from every aviation regulator on Earth. And that's where the real drama begins. The folding wingtips on the 777X are small in concept but huge in effect. Each outer wingtip section is about 3.5 meters, roughly 11 to 12 feet. In flight, the tips are extended to give the wing its full 71-meter span. On the ground, the tips fold up and the wingspan drops to roughly 64 to 65 meters, keeping the airplane inside Code E gate footprints. That difference is what lets airlines park a 777X where they already park a 777. Mechanically, it's clever and conservative. The folding system is an actuation stack, electric hydraulic motors made to aerospace standards, robust mechanical locks, and a web of sensors and interlocks. Pilots and ground crews don't play roulette with it. There are cockpit indications, warning lights, logic interlocks, and procedures so the airplane won't take off if the locks aren't confirmed. The idea is simple. If the system can't verify locked and safe, it throws a hard-to-ignore alarm and takeoff is inhibited until cleared. Why fold up instead of down? Folding upward avoids ground clearance problems. It clears the equipment and service vehicles, and it meshes better with composite wing behavior under load. The hinge and lock see predictable tension compression loads when the wing bends in flight. Upfolds also keep the locking hardware mostly in compression tension paths that engineers can design to be inherently fail-safe. Useful lesson borrowed from naval aviation. Folding mechanisms must lock so securely that under flight loads, nothing can unlatch. Because no existing certification fully covered a huge folding civil wingtip, regulators required special conditions. Boeing had to show the tip's load carrying capability, prove handling if a tip were wrongly positioned, and demonstrate fail-safe behavior during all phases of flight. The FAA formalized guidance on how airports should accommodate the airplane and what verification steps operators must follow. Here's where the folding tips stop being a gimmick and become an economic weapon. A longer span raises the wing's aspect ratio, cutting induced drag, the vortex-driven drag that dominates at the low lift coefficients of cruise. For transoceanic trips, that adds up. Less drag at cruise means lower thrust, less fuel burn per hour, and crucially, fewer dollars spent per seat. So, how much better is the 777X? Boeing and independent analysts placed the 777X's advantage over the 777-300ER in the 10 to 20% range on a per-seat fuel burn basis, depending on configuration and mission. Independent coverage typically narrows that to about 10 to 15% overall fuel burn improvement, with per-seat figures higher because the 777X can carry more passengers in efficient layouts. The extended wing, the thing the folding tips enable, is a big chunk of that improvement. Remove span and you remove most of the aerodynamic gain. The new platform, reduced sweep, and composite aeroelastic tailoring amplify the effect. Composite wings can be shaped so lift is distributed more evenly along the span, and they can be tuned to bend in ways that help reduce vortex strength. All of this works together. A longer, smarter wing makes a quieter, more fuel-efficient cruise package. Let's make it concrete with a script-friendly work example. Take a representative transatlantic cruise where a 777-300R might burn around 7,500 kilograms per hour. Ballpark, mission dependent. A 12% reduction, a mid-range number, equals 900 kilograms per hour saved. Over a 7-hour flight, that's 6,300 kilograms of jet fuel not burned. At a conservative jet fuel price of roughly $2.10 a gallon, roughly 55 cents a liter, regional and daily prices vary. That's 6,300 kilograms, roughly 8,000 liters, density around 0.8 kilograms per liter, which is roughly $4,400 saved on that single flight. Multiply by airline utilization, hundreds of flights per year per aircraft, and you see how the numbers scale into tens of millions of dollars across a fleet. Fuel prices and fuel burn vary by route and time of year. This is a worked example, not a guarantee. When people first hear folding wingtip, the natural fear is simple. What if it folds in midair? So let's address that head on. Boeing and regulators built layer after layer of protection to make that scenario as close to impossible as modern engineering allows. The 777X uses a multi-stage locking system. Once the wingtips extend, heavy mechanical locks clamp into place, backed up by redundant actuators and multiple independent sensors. The cockpit won't just assume everything's fine. The aircraft verifies several separate confirmations before it even lets the pilots continue. If a lock doesn't register, the jet throws up warnings, inhibits takeoff thrust, and won't let the crew roll down the runway with an unlocked tip. Structurally, the hinge itself isn't a weak point. The wing box and folding section use redundant load paths, shear fittings, and fail-safe joints designed to transfer bending and torsion loads even if a part of the mechanism malfunctions. That's why Boeing had to prove to the FAA and EASA that the wing could still handle flight loads even with simulated failures. Regulators also required Boeing to demonstrate how the aircraft behaves if somehow a tip stayed folded or partially extended on takeoff. Test pilots flew sims modeling asymmetric lift, drag, and control authority. The goal was to ensure the aircraft remains controllable long enough to safely land. Airlines also get defined procedures for handling any abnormal indication. Maintenance plays a massive role too. The hinge points, actuators, lock surfaces, and sensors all have higher frequency inspection intervals. MTBF targets for components are set extremely high, meaning the system has to demonstrate long failure-free operation cycles before certification. Interestingly, folding wings aren't new. Naval aviation has used them for decades. Jets like the FA-18 fold their wings hundreds of times in their lifetime, and that experience feeds directly into Boeing's civil-certified design philosophy: heavy locks, simple mechanisms, and redundancy everywhere. Long-haul jets live or die based on one thing: airport compatibility. Gates, taxiways, jet bridges, they're all built around fixed geometry. Most airports are designed for Cody wingspans, a category of aircraft like the 777-300ER and 747-400. Once you go beyond that, like the A380 did, airports must upgrade to Code F, and that's expensive, time-consuming, and often simply not possible. The 777X dodges that entire problem. On the ground, the folding tips bring the wingspan back down to Code E, meaning airlines can slide the 777X straight to their existing gates without modifying a single parking stand. Same tugs, same taxiways, same terminal spacing. That alone saves airlines millions in avoided infrastructure changes. Operationally, the sequence is simple. After landing and clearing the runway, the tips fold up. The process takes roughly 20 seconds. On departure, the pilots extend them before taxiing. Airlines can define their own SOPs, but typically the flight crew handles extension and retraction, with ground crew visually confirming from the ramp when needed. Economically, the folding wingtips might be one of the smartest compromises Boeing has ever engineered. Instead of forcing airports to adapt or shrinking the wing and losing efficiency, Boeing let the plane shapeshift depending on where it is. Airlines get the aerodynamic benefits in the air and the gate compatibility on the ground, a rare win-win in commercial aviation. Want more inside looks at the world's most advanced jets? Subscribe now and turn on notifications so you never miss a jet logic breakdown. To understand why folding wingtips matter, you have to look at the problems large wings have caused in the past. Not for drama, but for context. Start with the A380. Its massive wingspan pushed it into Code F territory, which meant airports had to widen taxiways, modify gates, and rework apron layouts just to host it. Dozens of airports couldn't justify the cost. If the A380 had a folding tip design, its ground footprint would have been smaller and far more airports could have supported it. But that technology wasn't feasible at that scale at the time, and Airbus chose simplicity over mechanical complexity. Wingtip collisions are another area where the 777X's design could have changed outcomes. There have been multiple instances across 777s, 747s, A330s, and A350s where aircraft clip poles, parked vehicles, or even other planes while taxiing in tight spaces. Reduced ground span doesn't eliminate that risk, but it lowers it by shrinking the part of the aircraft most likely to make contact. That's a real operational advantage. But let's be honest, some incidents wouldn't have changed at all. Most major structural or system failures in the 777 family, like UA328's engine failure, had nothing to do with the wingspan. Folding wingtip offers no protection from engine fan blade failures, hydraulic issues, or automation errors. It's a solution for ground compatibility and aerodynamic performance, not a cure-all for aviation problems. So, what's the real takeaway? Folding wingtips help avoid certain ground incidents, could have eased infrastructure headaches for aircraft like the A380, and offer airlines greater flexibility. But they aren't magic, just a smart, targeted solution to a very specific set of challenges. Folding wingtips aren't free. Boeing had to add actuators, hinges, locks, sensors, wiring, and structural reinforcement, all of which add weight and procurement cost. But Boeing's bet is simple. The fuel savings from that huge high aspect ratio wing will pay for the system many times over across a 20 to 25-year service life. And for airlines running long-haul routes daily, that math can be extremely favorable. Maintenance is where operators pay extra attention. Hinges, lock mechanisms, and actuator components need scheduled inspections. Operators factor in replacement parts, lubrication cycles, borescope checks, and occasional on-wing repairs. But when airlines run the numbers, the picture's usually clear. The 777X saves, say, 6 to 8% fuel in a long-haul flight compared to a 777-300ER. That could mean tens of thousands of dollars saved per month per aircraft. Even after adding a few extra maintenance man-hours and part costs, the payback horizon is typically short, especially for high-utilization fleets flying transoceanic missions. Another underrated benefit is residual value and deployment flexibility. Because the 777X fits into Code E gates, airlines can rotate it across more destinations without worrying about airport upgrades. That flexibility boosts utilization, and higher utilization means better long-term financial performance and higher resale value down the line. Airbus took a different path. The A350 and A380 were designed within conventional wingspan limits, or in the A380's case, Airbus simply accepted that airports would need to adapt. Instead of folding tips, Airbus focused on optimized wing shapes that fit gate constraints or served a different market philosophy entirely. But the landscape is shifting. Airbus has been exploring folding wing concepts for future narrowbody aircraft, including research models where only the outer portion folds to boost aerodynamic efficiency without breaking airport compatibility. It's still conceptual, but it shows the industry's paying close attention to Boeing's move. The real story is the strategic difference. Boeing looked at fuel efficiency, airport limitations, and market expectations, then decided a mechanical fold was the only realistic way to get a truly long, high aspect ratio wing into global operations. Airbus historically chose a simpler fixed-wing approach, optimizing within existing geometry. Neither strategy's wrong, they just reflect different assumptions. But now that the 777X has normalized folding wingtips in commercial service, it opens the door for future designs to go even further. Longer wings, more aeroelastic tailoring, and possibly hybrid adaptive surfaces might all become standard as manufacturers choose every percentage of fuel savings. The industry is watching closely and taking notes. Because folding wingtips weren't part of existing transport regulations, Boeing and global regulators had to create a whole new framework. The FAA and EASA issued special conditions spelling out every scenario the aircraft had to survive, from structural overloads to abnormal operations like attempting takeoff with an unlocked tip. Boeing had to prove the hinge and lock system could handle full aerodynamic loads with huge safety margins. They also had to demonstrate that even in the unlikely case of an unlocked tip, pilots could still control the aircraft long enough to land safely. That meant extensive simulation, ground testing, and flight validation work. Another key requirement was indication and interlock reliability. Regulators demanded redundant sensors, foolproof cockpit messaging, and logic that physically prevents takeoff if the wingtips aren't confirmed locked. Maintenance procedures also had to be codified so inspectors know exactly what to check and how often. FAA engineering briefs and EASA rulemaking documents essentially became the blueprint Boeing had to follow. A certification process tougher than almost any other modern aircraft feature, and a system designed to survive multiple layers of both mechanical and human failure. The biggest long-term impact of the 777X folding wingtips isn't the wings themselves, it's what the idea unlocks. For the first time, designers can chase ultra-efficient wings without being chained to airport geometry. You can build a long, slender aerodynamic wing for cruise efficiency and simply fold the part that causes problems on the ground. It's a major shift in how wide bodies might be designed going forward. Airlines also benefit in a big way. Future high-efficiency aircraft can serve more airports without forcing terminals to expand or taxiways to widen. That translates into more route flexibility, lower infrastructure pressure, and the ability to deploy big aircraft into places that previously couldn't host them. Of course, added complexity comes with trade-offs. More moving parts means more training for pilots, ground staff, and maintenance teams. Troubleshooting becomes more specialized, but for most operators, the fuel savings and operational reach will outweigh those challenges. In the long run, the 777X may be remembered not just as a new airplane, but as the moment when variable geometry made the jump from military decks to mainstream commercial aviation. Thanks for flying with JetLogic. If you enjoyed this look at the 777X's folding wings, like, subscribe, and share. We've got even more aviation stories coming your way.